Hello, Chem 101 students. I'd like to welcome you back for week 3 of our Chem 101 class. We've just finished talking about last week about units and measurements. We have one more type of unit to talk about this time, and it's going to be related to energy. So that was one type of measurement that we didn't get to. This is going to be focusing on the sections of your textbook, which are 7.1 to 7.2 in the textbook. And so it will be week 3 for us, and then we're going to move back into going back to chapter 3 here. We're going to talk about energy and the units associated with energy, a concept called the specific heat or specific heat capacity, more specifically, which is basically how much energy it takes to change the temperature of a substance. And we'll also talk about calories. So calories are the ways we usually talk about energy that we use in our body. And so I'll relate the energy units that we're talking about here to the kinds of dietary calories that you're used to thinking about in terms of biological energy. Okay. So what is energy? Well, what does it mean? Well, energy is the stuff of the universe that isn't matter. It's the ability to do work, work is defined as moving a mass over a particular distance. And so the units for energy are joules. They're indicated by a capital J, as you see right here, a capital J. But the unit you're probably more familiar with in terms of energy is calorie. So there's also a calorie in science. The calorie isn't quite the same as a dietary calorie. We'll talk about the similarities and differences near the end. But calorie is usually indicated with a cal, with a lowercase c. That's important. And the way calorie and joule are related is this way. 1 calorie is 4.184 joules. You don't have to memorize that. If you need that, I'll provide that to you. But you think of energy probably in the same way. If you want to move something like this guy here is moving this rock, you're going to need to eat something to have energy to move that rock, right? So energy is just generally defined as what it takes to move some things around. And we'll go a little bit more into energy later on, but we're just introducing the units now and the basic meanings of these things. So one thing that we'll be interested in is how much energy it takes to change the temperature of something. So you probably know that, let's say you're going to go and cook something on your stove. So you take a pot and you put it on the stove and you start heating it up. And the pot itself, which is made out of metal, heats up really fast. Then you put water in it, though. Let's say you're gonna boil some water to make some pasta or something, and that takes forever. And so you may be wondering, why is it that the pot feels hot so fast, but the water, it takes a while before it feels hot? This has everything to do with the heat capacity of water. Water has a high heat capacity, meaning that it takes a lot of heat energy to change the temperature of water. But the metal pot probably has a much lower heat capacity, so it takes a lot less energy to change the temperature of that pot. So this relationship is given by this equation. The heat that it takes to change the temperature of something is equal to the mass of that thing in grams times the specific heat, which is a constant, which you would always be given, and it differs for each substance, times the change in temperature that is occurring in this substance. And it's indicated like this: Q equals mc delta T. So the Q here is the heat, the Q is the heat, the M is mass, the C is specific heat here, and the delta T here is the change in temperature. Okay. And so, and I'm going to erase that. It's kind of ugly, but you get the idea here. The heat is Q, The mass is m here. The C stands for the specific heat, and the delta T means change in temperature. Delta means change, the Greek symbol delta. So what the specific heat, or the specific heat capacity as it's also called, is defined as is the amount of heat energy that it takes to raise the temperature of 1 gram of a particular substance by 1 degree Celsius. So let's look at some specific heats for some common substances. Here they are in joules. So water has a specific heat capacity at 4.18 approximately joules per gram per degree Celsius. So that means it takes 4.18 joules of energy to raise the temperature of 1 gram of water by 1 degree Celsius. Now what you'll see is wood has a significantly lower heat capacity. It's 1.76 joules. But iron and many metals have a much lower heat capacity. At iron, it's 0.46 joules of energy is what it takes to raise 1 gram of iron by 1 degree Celsius in temperature. So you can see that this is why when you put your iron pot, or maybe it's aluminum or something, you put it on your stove, it doesn't take much time or much heat being put in for it to increase in temperature a lot, because the iron has a much lower heat capacity. In fact, iron is much higher even than aluminum. And in terms of calories, for calories, it's 1 calorie for water, and that's where the calorie measurement for energy comes from. 1 calorie comes from the fact that it takes 1 calorie of energy to raise the temperature of 1 gram of water by 1 degree Celsius. And remember, these are not dietary calories. Dietary calories are actually 1,000 times bigger than this science calorie, but we'll talk about that nearer to the end of this lecture. So let's take a look at doing a problem like this now, where we use a specific heat and we figure out how much heat it takes to change the temperature of something like iron. So let's say we have this question: how much heat is required to change a temperature of 45 grams of iron from 25 degrees Celsius to 85 degrees Celsius? And we're going to use Q equals mc delta T. Now what we'll probably want to do is figure out what delta T is first. So delta T is the change in temperature. This means it's the final temperature minus the initial temperature. So our final temperature here was 85 degrees Celsius, and our initial temperature was 25 degrees Celsius. And so if we take the difference between these, we get 60 degrees Celsius. And make sure to put your decimal point here to remind yourself that this 0 is significant. We're subtracting, right? And so we look at the place value, ones place, ones place. Our last sig fig is at the ones place. So our 60 has 2 sig figs in it, the 6 and the 0. So now we're going to plug in all of these amounts here that we've got. We've got 45 grams of iron, and its specific heat is 0.46 joules per gram per degree Celsius. And we're going to multiply that by the change in temperature, which is 60 degrees Celsius. And I want you to take a look at what's going on with the units here. So you'll see that the units, we have units on the bottom. This is gram on the bottom, but we have grams on the top here, so those cancel. And then we've got degrees Celsius on the bottom here, and those cancel with degrees Celsius here. So we get units of joules, which is great. Okay, so now we should take out our calculator here, and we should multiply these. So 45 times 0.46 times 60, and this gives us 1,242. So our Q, or our heat required here, was 1,242. But that's not what we're going to write down. Don't forget your unit is joule. Remember, we have to look at what is the last sig fig. So we're multiplying. The 45 has 2 sig figs. The 0.46 has 2 sig figs. The 4 and the 6, because zeros in front are never significant. And the 60, I better make sure I write that with a decimal point, which I forgot to. But I better make sure to include that decimal point here, because that tells me this 0 is significant. So we have 2 sig figs there too. So our answer should be rounded so that it has 2 sig figs. It should be where the 2 is. So my final answer is going to be Q equals 1,000, I can put a comma here, 200 joules, because I rounded down. Since we had a 4 here, I rounded the 2 down, and I put 1,200. Don't forget to write the placeholder zeros. They're not significant digits, but they are important to make the number big enough. If you don't write them, your number will be too small. And that's the answer, 1,200 joules. So heat equals mass times specific heat times temperature change. So MC delta T, which is what we did right there. And I have on the next slide, I have the same answer that I typed here, or that I wrote out for you guys. 2 sig figs in the answer. So that's how you do a specific heat type of problem. And that's showing you how energy and temperature are related. Note they're not the same thing, right? Energy and temperature are different things. If you put in heat energy, you can change the temperature. Now you may be thinking, we define energy as the ability to do work, to move things. Well, remember back when we were in the first week, we talked about, or actually last week, we talked about what temperature is. Temperature is the average speed of the little pieces or molecules, the little pieces that are in our matter here, our stuff. And so actually what's happening is those little pieces are moving faster. So the movement that is happening is actually on a microscopic scale. So heat energy is basically the movement of all the little tiny pieces that make up all the stuff of the world. And so that's why we can still relate it back to moving things over a distance. They're just really tiny things. And they're moving faster when the temperature is higher. But this relates the fact that we need a certain amount of energy to change the temperature of a substance by a certain amount. And that temperature is not the same. It depends on what the stuff is. Remember, for water, it takes a lot more energy to raise the temperature than it does for this iron that we just did here. Okay. Now let's move on to dietary calories here. Oh, I thought they said this was a free image, and now I get one with a watermark. I didn't notice that before, but this is a nutrition label here. It has calories on it, and so hey, you might be thinking, we've been talking about calories, right? Well, these are a different type of calories. They are related. So the dietary calorie is often indicated with a capital C. So dietary calories are written in this way, cal, capital C, cal. We've been writing the other sciencey calories with a little c, cal. They're similar, they're related, but they're not exactly the same. Dietary calories are actually 1,000 science calories. They're a kilocalorie. Why? Well, it's because if they weren't, this label here would say, instead of saying 250, it would say 250,000 calories. That's the little calories. The big C calories are 250. They're 1,000 times larger rather, so you get 1,000 times smaller of a number here. I think it's because no one wants to, look at their cereal and see this bowl's gonna have 250,000 calories, right? It's an ugly number, it's big, and it's not convenient. So dietary calories are actually kilocalories, 1,000 science calories. So one dietary calorie, big C, is 1,000 calories, little c. It's 1 kilocalorie. In terms of macronutrients that we eat, so the macronutrients are proteins, carbohydrates, and fats. That's where we get our calories from, for the most part. how many calories are in a certain amount of protein or carbohydrates? Well, approximately to 1 sig fig, which is about as best we can do, because the way everyone absorbs calories is a bit different. It's going to vary, but 1 gram will give you about 4 calories, 4 dietary calories, 1 gram of carbohydrates, that is, of energy. When you metabolize 1 gram of protein, that will also give you about 4 dietary calories of energy. And if you process 1 gram of fats, this will give you about 9 dietary calories of energy. So all of this here that you see, they don't talk about it much in your textbook, but I think it's really interesting, especially since a lot of you are interested in health and nutrition and the health profession. It's really interesting to apply our discussion of energy here with dietary calories. But remember, the really important point is that a dietary calorie and a calorie in science, the little c calorie, are different things. So keep that in mind. But given that, we can do a few interesting calculations with calories. You may notice here that when you look at a food label, it breaks it down into how many grams of fat you've got, how many grams of carbohydrates you've got, and then underneath here somewhere would probably be the grams of protein. So we could actually figure out how each of these contributes to the overall calories. So altogether, the fats, the carbohydrates, and the protein should all give you altogether 250 calories. So let's see how that works out for some basic processed food here, like a Slim Fast bar, which isn't the healthiest thing. You can probably tell because it has a lot of carbs. There's nothing wrong with carbs if you need a lot of energy, but if you don't, it's kind of a lot of carbohydrates. If you're just going to be, watching TV, you probably don't need so many carbohydrates. We'll talk more about what fats, carbohydrates, and proteins are when we get to biochemistry at the end. We build up to talking exactly what kinds of atoms those things are made out of and how they're arranged and how they exist in the body. But we've still got a ways to go before we can do that. But we can talk about how many calories you get from fats and carbohydrates and proteins. So if you look at the label of a Slim Fast bar, it'll have around 5 grams of fat, 34 grams of carbohydrates, 8 grams of protein. And so if we want to figure out how many calories are in it, well, we have to keep in mind what these are. So I'm going to do this quickly, and then I'm going to do one all together after this. We have 5 grams of fat, and remember there were 9 calories for 1 gram of fat. So here our grams of fat are going to cancel. If we multiply 5 times 9, we get 45 calories. We've got 34 grams of carbohydrates, so we're going to put that on the next line. And there's 4 calories in 1 gram of carbohydrates, so our grams of carbohydrates cancel, and we multiply 34 times 4. We can use our calculator for that. 34 times 4, and we get 136 calories. And these are dietary calories, big C. Finally, we've got 8 grams of protein, and each gram of protein gives us 4 dietary calories. And so the grams cancel, we get calories. We have 132 calories, or sorry, we have 32 calories. And so if we want the total calories, we add these all up. And so we'll add 45 plus 136 plus 32, and we get a total of 213 calories. Now, you don't have to worry too much about sig figs on these. The reason why I say that is because we probably know calories to more sig figs, but it kind of varies. All calorie estimates they're estimates because everybody metabolizes food a bit differently. And so I say, if you go for these, you just go to the nearest whole dietary calorie. That's fine if I ever give you one of these on your homework or whatever. On the one on the homework, just go to the nearest calorie. It's fine. Don't worry too much about the sig figs here. We're just doing a rough calculation for these for interest, to give you guys a kind of idea of how calories relate to dietary calories. Okay, and then there's one other question we might be interested in. If I go back to the last slide, you'll see that we also have how many grams of each of these fat, carbohydrates, and so forth there are. We may want to know what percentage of the calories that we are getting are due to one particular type of macronutrient. Like maybe we don't want carbs to be too high of a percentage or something like that. So let me just remind you, what does percentage mean? So a percent of anything is the part that you're interested in over the whole thing. Okay, percent of whatever. It's the part you want to know over the whole thing. And then you multiply it times 100%, which will turn it into a percentage, okay? So if we want to know the percentage of a particular type of calories here, we take the part that is the one we're interested in, divide it by all of the calories, which are 213, and multiply it by 100%. That's what a percent is. It's the part over the whole. You get a fraction, and you turn it to a percent. So what is the percent of the calories from fat in the Slim Fast bar? Okay, well, if we go back and look, what we'll see if you look at the last slide, you could go back real quick in the video if you wanted to, but we had 45 calories from the fat, and we had 213 total calories on the last slide. And these are dietary calories, big C, make sure to put that big C. So we're going to put the part that we're interested in, which is the calories from the fat, we're going to put that on top, because that's what we're interested in. We're interested in the calories from the fat. So we put the fat calories on top, and then we divide that by the whole thing, all the calories. Now this will give us a fraction. Let's go ahead and calculate that fraction. 45 divide by 213. So what I mean by a fraction is this gives us a number that's less than 1. Of course, because the part can never be bigger than the whole thing. So your number here in this is always going to be a number less than 1, a fraction of 1, right? 0.211 we have here. So for that reason, we multiply that. So this was, we calculated it, this here was just to kind of do an in-between calculation. This was 0.211, but this is not a percentage yet. If we want to make it a percentage, we have to multiply times 100%. So when we multiply times 100%, we treat 100%, we treat percent like a unit. So you multiply 0.211, let's say, times 100, and you get 21.1, or we can do 21%, that's fine. Let's say this 45 has 2 sig figs. Like I said, I'm not going to be real picky about sig figs on this type of problem because of the way metabolism works. We can't really be that exact anyway. But we're going to have around 21%. Okay, so the percent stays. So when we do this, we have 45 divided by 213. Our calories cancel. So calories cancel. And we're just multiplying by 100%. So the unit that we keep is percent. Notice percent there. That's why if you ever want to turn something into a percent, just multiply it by 100%. You get your number, which was 21 for us, 21.1, around 21, and then you keep the percent like a unit. It just stays. If you ever want to add a percent on the end, multiply by 100%. Why can you multiply by 100%? Because think about what percent means. 100% means, what this means is actually 1 over 100. That's what percent means, per 100. So 100% is the same thing as saying 100 per 100. That is 1. So just like our conversion factors, you can always multiply or divide by 100% because it's like multiplying or dividing by 1. Just remember to keep your percent. Okay, that's pretty important. If you put a percent on there, it stays. We can also get rid of percent. If we wanted to go backwards and get rid of the percent, we divide this by 100%. Well, that would cancel the percent, and then that would give us just the number 0.21 without a percent. Okay, but that's not what we were doing here. Okay, we were actually wanted the percent. That's why we multiplied by 100%. So we get 21%. So let's do one more of these. How many calories are in a Nutrigrain bar? So this is, you'll notice a Nutrigrain bar and a Slim Fast bar aren't really that much different from each other. They're almost the same thing, even though they have very different sounding names. So what are we going to do here? Well, we just keep in mind we've got 3 grams of fat. We want to convert those to how many calories there are, and 1 gram of fat is 9 dietary calories. So we're going to get 27 calories from the fat. And then we've got 27 grams of carbs. And we know 1 gram carb. So notice what I'm doing here. I'm doing the same exact strategy that we used when we were doing conversions in the last chapter. I make sure that my old unit cancels and I get calories, which is the unit I want, right? Same thing here. This cancels. Just make sure the other side of my conversion factor is correct. Should be 1 gram of carbs gives you 4 calories. Okay. And so we'll have 27 times 4. 27 times 4 equals 108. 108 calories. Okay. And finally, 2 grams of protein. And that was 1 gram of protein was also 4 calories. And so our grams of protein will cancel and we'll get 8 calories. Okay. And now to get the total calories, we add these all up. We add them up. It's 27 plus 108 plus 8. Whoops. 27 plus 108 plus 8 equals 143 calories. So altogether, these are 143 calories. Okay. So I just typed the same thing here and just kind of gave you a little bit of a better look there, how we're canceling our grams, we're getting calories. And now let's say I ask you, what is the percent of calories from fat in the Slim Fast bar? Okay, let's go back. We had 27 calories from fat, 143 calories total. 143 calories total. Remember, percent means the part over the whole. So the part, and then times 100% to make it a percent. So the part that we're interested in is the calories from the fat. That's going to go on top. We're going to divide by the whole thing, the total calories, and we're going to multiply times 100%. So percent of calories from fat is going to be 27 calories up here, divided by 143 calories down here, times 100% to make it a percent. And so our math goes 27 divided by 143 times 100. And so we get about 19. And don't forget the percent, 19%. Okay, because when you multiply times 100%, you want to treat that number like a unit. The calories cancel. We end up with just the unit percent, and that's why you see it right there. Okay. And so that's been the lecture about energy. I hope this was interesting to you, especially those of you interested in nutrition. Tried to give a little application there. For our next lecture, we'll start to talk about atoms. And so I will see you in that one.